universe, in its current state, maintains a background temperature of 2.726 degrees Kelvin. This is just under 2.73 degrees above the coldest temperature that can physically exist. That radiation fills everything. It reaches every point in space, permeating the gaps between galaxies, settling into the vast stretches between stars, existing in the darkness we sometimes imagine as absolute nothing. This temperature represents something profound. It is the cooled remnant of the first light that could travel freely through space, released when the universe was only 380,000 years old. Back then, that same radiation was intensely hot, a blazing glow filling everything. But 13.8 billion years of expansion have stretched it, cooled it, transformed it into something gentle. Now it manifests as microwave radiation, invisible to human eyes, barely detectable even with sensitive instruments. Yet it is always there, a background hum of existence, the echo of the universe's earliest moments when matter and light finally separated. You cannot escape it. In the darkest void between galaxy clusters, in the emptiest regions of intergalactic space, this radiation persists. It provides a baseline, a floor temperature for reality itself. Nothing in the universe can naturally cool below this point, not without active intervention. The cosmos refuses to become colder than its own ancient memory. Scientists measure it with extraordinary precision. The temperature is not exactly uniform across the sky. There are tiny fluctuations, variations of only a few millionths of a degree. These minute differences, these almost imperceptible temperature changes, represent the seeds from which all cosmic structure would eventually grow. The slightly warmer regions corresponded to areas of slightly higher density in the early universe. Over billions of years, gravity would amplify these differences, pulling matter together, forming the first stars, then galaxies, then clusters of galaxies. All the structure we observe today, all the galaxies and their contents, trace back to temperature variations so small they challenge the limits of measurement. The discovery of this background radiation came by accident. In 1965, two scientists working with a large horn-shaped antenna were trying to eliminate an annoying static that kept appearing in their data. They cleaned the antenna, they checked for interference, they even cleared out pigeons that had nested inside, removing what they politely called dielectric material from the equipment. The static remained, coming from every direction equally, persistent and unexplainable. What they had found, without initially realizing it, was evidence for the Big Bang itself, the remnant glow of creation still washing over Earth 13.8 billion years later. They would share a Nobel Prize for this discovery, for finding the universe's background temperature by accident while trying to eliminate what they thought was noise. The uniformity of this temperature reveals something fundamental. No matter which direction you point your instruments, the reading comes back essentially the same. This uniformity tells us that the early universe was remarkably smooth, that matter and energy were distributed almost evenly across vast distances. The small variations that do exist are what make the universe interesting, but the overwhelming characteristic is sameness. Turn your detector north, south, toward the constellation Virgo or toward the constellation Cetus, the result remains within a few millionths of a degree of 2.726 Kelvin. This radiation does not require stars or galaxies to exist. It is independent of any particular object. It fills the universe simply because the universe exists, because space itself expanded and cooled from an initially hot, dense state. Every cubic centimeter of space contains about 400 photons of this microwave radiation. They travel in all directions, crossing paths, creating a bath of energy that has been cooling for the entire history of the universe and will continue cooling as expansion continues. The temperature will keep dropping. As the universe expands further, this background radiation will stretch to longer wavelengths corresponding to even lower temperatures. Billions of years from now, it will be cooler than it is today. Trillions of years from now, cooler still. The expansion of space ensures that this cooling never stops, that the universe gradually approaches but never quite reaches absolute zero, always retaining this faint warmth, this memory of its fiery beginning. When you think about temperature in space, this is the minimum. This is what empty space feels like when nothing else interferes with it. Not cold in any familiar sense, but possessing a definite temperature nonetheless, measurable and real. In the regions between galaxies, far from any stars, far from any source of heat, space maintains this temperature. Not frozen solid, because there is essentially nothing there to freeze, but defined by the energy of these ancient photons still traveling after more than 13 billion years. The precision of the measurement matters. Scientists can now measure this temperature to within about 1/1000th of a degree. The current best measurement stands at 2.7260, plus or minus 0.0013 Kelvin. This level of precision required space-based observations, instruments floating above Earth's atmosphere, where interference from our planet's own radiation would not contaminate the measurement. Satellites like the Cosmic Background Explorer and the Planck spacecraft map the temperature variations across the entire sky, creating images that show the universe as it appeared 380,000 years after the Big Bang. These maps reveal patterns. Those slightly warmer and cooler regions form a mottled texture across the sky, like looking at a distant wall with subtle variations in color. These patterns are not random. They reflect actual physics, the behavior of sound waves moving through the hot plasma of the early universe before atoms could form. The size of the largest warm spots corresponds to the distance sound could travel in 380,000 years, about 400,000 light-years. This characteristic size appears in the data, providing another confirmation that our understanding of the early universe aligns with observation. The existence of this background temperature connects the present to the distant past in a direct, measurable way. The photons reaching our instruments today have been traveling since the universe was less than 1% of its current age. They carry information about conditions back then, about the density and temperature of matter, about the composition of the cosmos. By studying these photons, we study the universe as it was billions of years before the sun formed, before our galaxy took its current shape, before the first generation of stars had even begun to die and scatter heavy elements into space. Nothing you do changes this temperature. You can travel to the emptiest part of the universe you can imagine, and it will still be there. You can wait billions of years, and it will still be there, just slightly cooler. This is the warmth of creation itself, diluted and stretched but never completely fading. A permanent feature of reality. The universe remembers where it came from, encoded in the wavelength of its oldest light. When we say space is empty, we mean something very specific. Between stars in our galaxy, in the regions astronomers call the interstellar medium, the density of matter averages roughly 1 million particles per cubic meter. That sounds like a lot, until you realize a cubic meter of air at sea level on Earth contains about 25 quintillion molecules. The interstellar medium is emptier than the best vacuum any laboratory on Earth has ever achieved. Yet even this is not truly empty. Those million particles per cubic meter represent a remarkable average. In some regions, cold molecular clouds can contain 100 million to 1 trillion particles per cubic meter. In other areas, hot ionized regions maintain densities as low as 100,000 particles per cubic meter. The variation spans orders of magnitude, yet even the densest interstellar clouds remain billions of times less dense than air. Most of these particles are hydrogen atoms. Approximately 70% of the mass exists as lone hydrogen, single atoms drifting through space, not bonded into molecules. Another 28% consists of helium. The remaining 2% includes every other element, all the carbon and oxygen and iron and gold, all the elements forged in stars, scattered by supernova explosions, gradually enriching the space between stars. This enriched material will eventually participate in forming new stars and planets, carrying forward the chemical legacy of previous stellar generations. The space between stars is not uniformly distributed. It organizes into structures: dense clouds where star formation occurs, bubbles blown by stellar winds from massive stars, shells expanding from supernova explosions, regions heated to millions of degrees by the energy of dying stars. All of this creates a complex, textured environment, but the overall density remains extraordinarily low by everyday standards. Between galaxies, the density drops even further. In intergalactic space, the average density falls to less than 1 hydrogen atom per cubic meter. That single atom might sit alone in a cubic meter of space, with the next nearest atom a meter away in some direction. In the vast voids between clusters of galaxies, the density can fall to just 15% of the average, meaning you might find only 1 atom for every 7 cubic meters of space. Consider the implications of this density. If you could somehow gather all the matter in a cubic meter of intergalactic space and compress it to the density of water, you would have a droplet smaller than a bacterium. The overwhelming characteristic of intergalactic space is absence, a profound scarcity of material that makes even the hardest vacuum on Earth seem crowded by comparison. Yet, this incredibly diffuse gas accounts for roughly half the ordinary matter in the universe. More atoms exist in intergalactic space than exist in all the stars in all the galaxies combined. The gas is just spread so thin, distributed across such vast volumes, that its total mass becomes substantial despite its low density. This intergalactic medium consists primarily of primordial hydrogen and helium, material that has never been inside a star, that has drifted in the space between galaxies since the early universe. The temperature of this intergalactic medium surprises most people. It is hot, millions of degrees in many regions. This seems contradictory for something so empty, but temperature measures the average energy of individual particles, not the total heat content. A single hydrogen atom moving very fast possesses high temperature, but if you put your hand in that location, you would not burn because so few particles would collide with your skin to transfer energy. The particles in intergalactic space move at tremendous speeds, giving them high temperatures, but their extreme rarity means they carry little total energy. Cosmic voids represent the emptiest regions we know. These are volumes of space that can span 100 to 300 million light-years where very few galaxies exist. The matter density in these voids falls to about 15% of the cosmic average, though even this reduced density still means billions of hydrogen atoms per cubic light-year. From within a void, looking in any direction, you would see almost no galaxies, just vast darkness punctuated occasionally by a distant, isolated dwarf galaxy. These voids are not completely empty. They contain the diffuse intergalactic medium. They contain the cosmic microwave background radiation. Neutrinos pass through them, cosmic rays traverse them. Dark matter, if it exists as current theory suggests, permeates them in even greater abundance than normal matter. The voids are not absence in any absolute sense, just regions where galaxies did not form, where the initial density of the early universe was slightly lower, where gravity had less material to work with. The structure of the universe on the largest scales resembles a foam or sponge. Dense filaments of galaxies outline the edges of voids. Where filaments intersect, galaxy clusters form. The voids themselves are the bulk of the volume. If you could see the entire observable universe at once, you would see a cosmic web with the voids as the negative space between the strands. This pattern emerged from tiny density fluctuations in the very early universe, amplified by 13.8 billion years of gravitational attraction. Even in seemingly empty space, virtual particles constantly appear and disappear. Quantum mechanics predicts that pairs of particles and antiparticles spontaneously form, exist briefly, and annihilate. This happens everywhere, all the time, even in the deepest voids. These virtual particles do not violate conservation of energy because they exist for such brief intervals that the uncertainty principle permits their creation. Empty space, at the quantum level, seethes with this activity, though it manifests in ways that do not create permanent particles or transfer energy across large distances. The emptiness itself is not nothing. Space possesses properties, it can expand, it can curve in response to mass and energy, it can transmit electromagnetic radiation and gravitational waves. Calling it empty describes the absence of matter and conventional energy, but space itself is something, a fundamental aspect of reality with its own characteristics. The universe is not objects floating in a void. The universe is the objects and the space between them, both essential components of what exists. When you consider how empty space really is, the isolation becomes striking. If you were floating in intergalactic space, the nearest atom might be meters away. The nearest galaxy could be millions of light-years distant. You would see perhaps a handful of galaxies in the sky, all extremely faint, all billions of light-years away. The cosmic microwave background would bathe you in its 2.7 Kelvin radiation. Otherwise, darkness. Silence, in the sense that no medium exists to carry sound waves. Just you, the ancient light, and the vast separation between everything that exists. This emptiness is ancient. The expansion of the universe created it. In the early moments, everything was close together, densities incomprehensibly high. As space expanded, the distances between things grew. Regions that were once near each other separated, becoming millions or billions of light-years apart. The expansion created more space, literally more volume, without creating more matter to fill it. The result is the emptiness we observe today, continuously growing as expansion continues, creating ever more space for matter to spread through. The average density of the entire universe, counting all the matter and dividing by all the volume, comes to roughly 1 proton per 4 cubic meters. That is the cosmic average, accounting for the dense regions inside galaxies and the nearly empty voids between them. 4 cubic meters is a volume 2 meters on each side, a box that could contain a small car. On average, that entire volume contains the mass of a single hydrogen nucleus. This is what the universe is mostly made of, considering volume rather than mass. Emptiness. Distance. Space itself, with the occasional atom drifting through it. The light reaching Earth right now from the most distant observable objects began its journey when the universe was very young. We see these distant galaxies not as they are now, but as they were billions of years ago. The light has been traveling all that time, crossing the expanding space between there and here, arriving finally at our instruments to tell us about conditions in the ancient cosmos. The cosmic microwave background radiation represents light from even earlier times. This radiation was released 380,000 years after the Big Bang, when electrons and protons first combined to form neutral hydrogen atoms. Before this moment, the universe was opaque. Free electrons scattered photons continuously, preventing light from traveling far. The universe resembled the interior of a glowing fog, everywhere bright but impossible to see through. Then, as the universe cooled below about 3,000 Kelvin, electrons combined with protons. Photons could suddenly travel freely. The universe became transparent. That moment is called recombination, though it would be more accurate to call it combination, since electrons and protons had never been together before. The photons released at recombination have been traveling ever since. They filled the universe at that moment, heading in every direction. Some of those photons, the ones emitted from regions very far from what would eventually become our location, are just now reaching us. We detect them as the cosmic microwave background. The current temperature of this radiation, 2.726 Kelvin, represents a tremendous amount of cooling from its initial 3,000 Kelvin. The expansion of space stretched these photons to longer wavelengths. What began as visible light, with wavelengths of hundreds of nanometers, has been stretched to microwave wavelengths measured in millimeters. This stretching is not because the photons are moving through space at different speeds. Light always travels at the same speed in vacuum. The stretching occurs because space itself expanded during the photons' journey, carrying them along, gradually increasing the distance between wave crests. We can calculate when this light was released by examining its properties. The temperature tells us about the expansion rate. The small fluctuations in temperature across the sky tell us about density variations in the early universe. These observations all point to the same conclusion. The cosmic microwave background was released 380,000 years after the Big Bang, when the universe was about 1/1100th of its present size. Everything was closer together. The density was roughly 1.3 billion times higher than today. The universe at recombination consisted mostly of hydrogen and helium gas. No stars existed yet. No galaxies had formed. The slight density variations visible in the cosmic microwave background would eventually grow into galaxies and clusters, but at 380,000 years, the differences were tiny, barely detectable. The universe was remarkably uniform, smooth to within about 1 part in 100,000. The fluctuations we measure in the background radiation reflect this smoothness. The temperature varies from point to point by only about 30 microkelvin, 30 millionths of a degree. The region of space that emitted the cosmic microwave background we see today is called the surface of last scattering. This is not a physical surface, not a boundary in space. Rather, it represents the set of locations far enough away that light from there, emitted at recombination, is just now arriving here. If we could wait another million years, we would see the cosmic microwave background coming from regions slightly farther away, from locations whose light took an additional million years to reach us. The surface of last scattering continuously recedes as we look at light from progressively more distant sources. This creates an interesting perspective on the observable universe. We can never see beyond the surface of last scattering using electromagnetic radiation. Before recombination, the universe was opaque. Any light emitted earlier was scattered and absorbed before it could travel far. The cosmic microwave background represents our ultimate visual horizon, the farthest we can see using light. Beyond that lies a period we cannot directly observe with telescopes, though we can infer what happened from theory and from other evidence, like the abundance of light elements formed in the first few minutes after the Big Bang. The photons of the cosmic microwave background have traveled a considerable distance. The regions that emitted the radiation we see today are now about 46 billion light-years away. This seems paradoxical at first. If the universe is only 13.8 billion years old, how can anything be 46 billion light-years away? The answer lies in expansion. When the photons began their journey, the distance to the emission point was much smaller, only about 42 million light-years. But during the 13.8 billion years the photons traveled, space itself expanded. The location where the photons originated moved farther and farther away as expansion continued. By now, that region has receded to 46 billion light-years from our position. This demonstrates an important aspect of cosmology. Distances in an expanding universe are not fixed. The space between objects increases over time. When we say an object is 46 billion light-years away, we mean that is its current distance, accounting for all the expansion that has occurred. The light travel time tells us how long ago the light was emitted, but the current distance depends on how much expansion has happened since then. Every direction we look, we see the cosmic microwave background at essentially the same distance. This makes sense because recombination happened everywhere at roughly the same time. The universe cooled uniformly, reaching the temperature where atoms could form at the same cosmic moment throughout space. What we see as the cosmic microwave background is just the light from the regions far enough away that their recombination light is reaching us now. Closer regions, we saw their recombination light billions of years ago. More distant regions, their recombination light has not reached us yet and will arrive in the future. The uniformity of the cosmic microwave background tells us the universe was expanding and cooling in a remarkably consistent way 13.8 billion years ago. Regions that are now on opposite sides of the observable universe, separated by 93 billion light-years, had almost identical temperatures and densities at recombination. This uniformity requires explanation, leading to theories like cosmic inflation that propose a brief period of extremely rapid expansion in the universe's first fraction of a second, smoothing out any initial irregularities. The study of the cosmic microwave background provides some of our most precise measurements of cosmological parameters. By analyzing the pattern of temperature fluctuations, their size and amplitude, we can determine the age of the universe, its expansion rate, its geometry, and the relative amounts of ordinary matter, dark matter, and dark energy it contains. All of this information is encoded in the light from recombination, waiting to be decoded by careful observation and analysis. Future observations will continue refining our understanding. New telescopes and more sensitive detectors will measure the polarization of the cosmic microwave background, which carries additional information about conditions in the early universe, including potential signals from gravitational waves created during inflation. Each improvement in measurement, precision constrains our theories further, helping us understand the first moments of cosmic history. The cosmic microwave background is not static. As the universe continues to expand, this radiation will continue to cool, stretch to longer wavelengths, become fainter. Eventually, billions of years from now, it will shift entirely into the radio portion of the spectrum, even harder to detect than it is now. The cooling never stops, just as the expansion never stops. The universe keeps creating more space, diluting the energy density of this ancient radiation, yet it will never disappear entirely. Barring some catastrophic event that destroys the fabric of space itself, the cosmic microwave background will persist for the indefinite future, always present, always detectable if you have sufficiently sensitive instruments. It is a permanent record of the universe's infancy, light that has outlasted the formation and death of countless stars, that was already ancient when our sun formed, that will continue existing long after our sun dies. The universe expands. This has been known since the 1920s, when Edwin Hubble observed that distant galaxies are moving away from us, with more distant galaxies receding faster than nearby ones. The relationship is linear, described by what we now call Hubble's law. The speed at which a galaxy recedes is proportional to its distance from us. Double the distance, double the recession speed. This pattern suggests the universe itself is growing, with space stretching between galaxies. Measuring the exact rate of expansion has proven challenging. The expansion rate is quantified by the Hubble constant, which tells us how fast space is stretching. Currently, the most precise measurements indicate the Hubble constant is somewhere around 70 to 73 kilometers per second per megaparsec. What this means is that for every megaparsec of distance, roughly 3.26 million light-years, the recession velocity increases by 70 to 73 kilometers per second. Consider an object 1 megaparsec away. It recedes at about 70 kilometers per second. An object 2 megaparsecs away recedes at 140 kilometers per second. An object 10 megaparsecs away recedes at 700 kilometers per second. The pattern continues. Sufficiently distant objects recede faster than the speed of light. This does not violate relativity because the objects themselves are not moving through space faster than light. Rather, space is expanding between us and them. Relativity limits motion through space, but places no restriction on how fast space itself can grow. The Hubble constant determines the age of the universe. If we run the expansion backward, we can calculate when everything was together at a single point. This calculation, combined with other measurements, gives an age of about 13.8 billion years. The precision of this measurement has improved dramatically. 50 years ago, estimates ranged from 10 billion to 20 billion years. Now we know the age to within about 1%. Different methods of measuring the Hubble constant have produced slightly different values. This discrepancy is called the Hubble tension. Observations of the nearby universe, using Cepheid variable stars and Type 1a supernovae as distance indicators, give values around 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background, using our understanding of the early universe to predict the current expansion rate, give values around 67 to 68 kilometers per second per megaparsec. The difference may seem small, but it is statistically significant. Both measurement methods have been checked and rechecked. The instruments have been calibrated carefully. The analysis has been scrutinized. Yet the tension persists. This could indicate we are missing something fundamental about how the universe works, perhaps new physics governing the expansion, or it could reflect subtle systematic errors in one or both measurement approaches. Resolving this tension is one of the major goals of current cosmology. The expansion rate was not always the same. In the universe's very early moments, during the period called inflation, space expanded exponentially, doubling in size every tiny fraction of a second. This lasted only a brief instant, perhaps 10 to the negative 35 seconds, but it stretched the universe by an enormous factor. After inflation ended, the expansion continued but at a much slower rate, governed by the gravitational attraction of matter and radiation. For the first several billion years, gravity gradually slowed the expansion. The matter in the universe pulled on itself, acting as a brake. If there had been enough matter, the expansion might have eventually stopped and reversed, leading to a big crunch. But observations in the late 1990s revealed something unexpected. The expansion is not slowing down, it is speeding up. This acceleration began relatively recently, about 5 billion years ago, when the universe was roughly half its current age. Something is pushing space apart, overcoming the gravitational attraction of matter. We call this something dark energy, though we do not really understand what it is. Dark energy appears to exert a kind of negative pressure, pushing space to expand faster rather than allowing gravity to slow the expansion. As the universe grows, dark energy becomes more dominant because its density remains constant while matter density decreases as space stretches. Current observations suggest dark energy makes up about 68% of the total energy density of the universe. Dark matter, another mysterious component we detect only through its gravitational effects, accounts for about 27%. Ordinary matter, everything made of atoms, everything we can see and touch, comprises only about 5%. The universe is mostly composed of things we do not yet fully understand. The expansion creates new space. This is worth emphasizing because it can be confusing. The expansion is not just objects moving farther apart through pre-existing space. Rather, the volume of the universe itself is increasing. New space is being created between galaxies. A ruler stretching between two galaxies would have to grow longer to maintain contact with both galaxies as they separate due to expansion. This expansion affects light traveling through space. As a photon travels from a distant galaxy toward Earth, the space through which it travels stretches. The wavelength of the photon stretches along with the space, shifting toward the red end of the spectrum. This cosmological redshift provides a direct measure of how much the universe has expanded since the light was emitted. If we measure a redshift corresponding to doubling of wavelength, we know the universe has doubled in size since that light began its journey. Extremely distant objects show large redshifts. The most distant galaxies observed have redshifts of 10 or more, meaning their light has been stretched by a factor of 10 or more, indicating the universe has expanded by that factor since the light was emitted. These galaxies appear as they were when the universe was less than 1 billion years old, less than 1/10 of its current age. Their light has been traveling toward us for over 13 billion years. The expansion rate can be expressed in different ways. In terms of scale factor, the universe doubles in size about every 10 billion years at the current expansion rate. This doubling time will continue to increase as dark energy drives accelerated expansion. In the far future, billions of years from now, the expansion rate will approach a constant value determined by dark energy, and the universe will expand exponentially, doubling in size at regular intervals. Galaxies, within gravitationally bound groups, do not participate in the expansion. The Milky Way and Andromeda galaxies, for instance, are moving toward each other, not apart, because their mutual gravitational attraction overcomes the expansion of space. On scales of millions of light years, galaxy clusters remain bound together. Expansion affects only the largest scales, the distances between galaxy clusters and superclusters. On these scales, gravity is too weak to hold things together, and expansion wins. The expansion has no center and no edge, at least not within the observable universe. Every location sees itself as the center with everything else receding. This is a natural consequence of space itself expanding. Imagine dots on the surface of an inflating balloon. As the balloon expands, every dot sees every other dot moving away, with farther dots moving away faster. No dot is special. No location is the center. The universe works the same way, though in 3 dimensions rather than on a 2-dimensional surface. The ultimate fate of the universe depends on the behavior of dark energy. If dark energy remains constant, the universe will continue accelerating, expanding faster and faster forever. Galaxies beyond our local group will eventually recede so fast that their light can never reach us, disappearing beyond a cosmic horizon. The universe will become increasingly empty and cold, with isolated islands of matter separated by ever greater distances. This scenario is called the Big Freeze or heat death. Other possibilities exist. If dark energy strengthens over time, it could eventually overcome not just the gravitational binding of galaxy clusters, but also of galaxies themselves. Then star systems, then planets, then molecules and atoms, ripping apart the fabric of matter in a big rip. If dark energy weakens or reverses, gravity might eventually halt and reverse the expansion, leading to a big crunch. Current observations favor continued acceleration, but the distant future remains uncertain. The expansion happens at a specific, measurable rate. For the observable universe, with a radius of about 46 billion light-years, the expansion adds about 1 light-year of radius every Earth year. The volume increases much faster because volume scales with the cube of the radius, but the linear expansion rate is remarkably slow, just 1 light-year per year. This slowness, combined with the vast scales involved, makes expansion imperceptible on human timescales. Stars do not drift apart. Galaxies in our local group do not separate. Only on the larger scales does expansion dominate. Near a black hole, time behaves in ways that challenge our everyday understanding. The intense gravitational field distorts not just space, but time itself, creating effects that seem impossible, yet follow inevitably from the equations of general relativity. An object falling toward a black hole experiences these effects directly, while an outside observer sees something entirely different. Both perspectives are valid, both describe the same events, yet they disagree profoundly about what happens and when. Consider an astronaut falling toward a black hole. From the astronaut's perspective, the journey seems unremarkable at first. Time passes normally. The spacecraft continues falling, accelerating as gravity pulls it closer. There is no barrier, no wall at the event horizon. The astronaut crosses this boundary without noticing anything special. The crossing happens in finite time from the astronaut's viewpoint. Once past the event horizon, the astronaut continues falling toward the center, toward the singularity. The entire journey, from a safe distance to the singularity, takes perhaps minutes or hours depending on the black hole's mass. From the perspective of someone watching from far away, the story is completely different. As the astronaut approaches the event horizon, time for the astronaut appears to slow down. The astronaut's movements become sluggish, then slower, then almost imperceptibly slow. Light from the astronaut becomes increasingly redshifted, shifting toward longer wavelengths, becoming redder and dimmer. The astronaut appears to freeze just above the event horizon, time for them seemingly stopped, their image growing darker and redder until it fades from view. The outside observer never sees the astronaut cross the event horizon. Both descriptions are correct. General relativity predicts this disagreement between observers in different gravitational potentials. Time is not absolute. It flows at different rates depending on the strength of gravity. Near a black hole, where gravity is extreme, time dilation becomes extreme as well. The effect becomes infinite precisely at the event horizon. At this boundary, time for an infalling object, as measured by an outside observer, stretches to infinity. The outside observer would have to wait forever to see the object actually cross the horizon. Meanwhile, the infalling object crosses in finite proper time, the time measured by a clock traveling with the object. This is not a contradiction. It reflects the fact that simultaneity, the concept of events happening at the same time, depends on the observer's reference frame. The mathematics of general relativity describes this precisely. The Schwarzschild metric, the solution to Einstein's equations for a non-rotating black hole, contains factors that become infinite at the event horizon. These mathematical infinities correspond to infinite time dilation. Time, as measured by a distant observer, stops at the horizon. But this is an artifact of the coordinate system chosen by the distant observer. Other coordinate systems, equally valid, show that the horizon is not special from the perspective of someone crossing it. The size of a black hole's event horizon depends only on its mass. For a non-rotating black hole, the radius of the event horizon equals approximately 3 kilometers multiplied by the mass in solar masses. A black hole with the Sun's mass would have an event horizon about 3 kilometers in radius. A black hole with 10 times the Sun's mass would have an event horizon of 30 kilometers. Supermassive black holes at the centers of galaxies, with masses of millions or billions of solar masses, have event horizons millions or billions of kilometers in radius. The strength of gravity at the event horizon depends on the black hole's mass in an interesting way. Larger black holes have weaker gravity at their event horizons. This seems counterintuitive, but follows from the fact that the event horizon grows proportionally with mass, while gravitational force falls off with the square of distance. For a stellar mass black hole of 10 solar masses, the gravitational acceleration at the event horizon would be about 150 trillion meters per second squared. For a supermassive black hole of 1 billion solar masses, the gravitational acceleration at the event horizon would be only about 1.5 meters per second squared, less than the gravity you feel standing on Earth's surface. This means you could, in principle, cross the event horizon of a supermassive black hole without experiencing extreme tidal forces, the differential pull of gravity on different parts of your body. The gravitational field changes more gradually for larger black holes. The event horizon is simply larger, and the difference in gravitational strength between your head and feet would be manageable. For a stellar mass black hole, the tidal forces would tear you apart long before you reach the event horizon. For a supermassive black hole, you might survive the crossing, though you would still be doomed once inside. Time dilation affects everything near a black hole, not just objects falling in. Imagine two spacecraft in orbit, one close to the event horizon, one far away. Clocks on the closer spacecraft run slower than clocks on the distant one. If the crews communicated by radio, sending signals once per second according to their own clocks, the distant crew would receive signals from the nearby spacecraft at a slower rate, perhaps one every 2 seconds. The nearby spacecraft would receive signals from the distant one at a faster rate, perhaps 2 per second. Both crews would notice these effects, but would disagree about whose clock was running slow. This effect has practical consequences for objects orbiting black holes. Accretion disks, swirling clouds of matter falling into black holes, emit light from different regions at different rates according to distant observers. Matter near the event horizon appears dimmer and redder because its light is severely redshifted and time-dilated. Matter farther out appears brighter and bluer. This creates observable signatures that astronomers use to study black holes, measuring the effects of time dilation on the light from infalling matter. Rotating black holes add additional complexity. A rotating black hole drags space-time around with it, creating a region called the ergosphere just outside the event horizon where nothing can remain stationary. Even space itself rotates within the ergosphere. Objects within this region must move in the direction of the black hole's rotation. They can still escape, unlike objects that have crossed the event horizon, but they cannot simply hover in place. The rotation also affects time dilation, creating even more complex relationships between different observers. The extreme time dilation near black holes makes them potential time machines, at least in theory. If you could somehow orbit very close to a black hole's event horizon and then return to a safe distance, less time would pass for you than for people who remained far away. You would emerge in their future. The practical challenges are enormous, requiring vast amounts of energy to establish and maintain such an orbit, and the gravitational forces would likely destroy any spacecraft. But the principle is sound. Time dilation is real, and extreme gravity can create large differences in elapsed time between different locations. Black holes also preserve information about the geometry of space-time in their vicinity. The event horizon itself is not a physical surface. Nothing material composes it. It is simply a boundary in space-time, a point of no return. Light, emitted exactly at the event horizon, directed outward, neither escapes nor falls in. It remains at the event horizon, trapped in an endless attempt to escape. This creates a mathematical surface, a boundary that can be described and studied even though it has no physical substance. The properties of this boundary are remarkable. The surface area of the event horizon can never decrease, at least according to classical general relativity without quantum effects. If two black holes merge, the resulting black hole has an event horizon whose area equals or exceeds the sum of the original event horizons. If matter falls into a black hole, the event horizon area increases. This behavior resembles the second law of thermodynamics, which states that entropy never decreases. The parallel led physicists to develop black hole thermodynamics, a framework treating event horizon area as analogous to entropy. This framework predicts that black holes should have a temperature, called Hawking temperature, related to their mass. Smaller black holes should be hotter. A black hole with one solar mass would have a temperature of about 60 nanokelvin, much colder than the cosmic microwave background. A black hole with the mass of a mountain might have a temperature of a few Kelvin. A very small black hole with the mass of a large asteroid might have a temperature of billions of Kelvin. These predictions come from applying quantum mechanics to curved space-time near the event horizon. Hawking radiation, the theoretical emission from black holes, represents a quantum effect. Virtual particle pairs that form near the event horizon can be separated by the intense gravitational field. One particle falls into the black hole while the other escapes. To an outside observer, the black hole appears to emit particles. This emission carries energy away, gradually decreasing the black hole's mass. The process is extraordinarily slow for any black hole formed from a collapsed star. A solar mass black hole would take about 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. Only very small black holes, if they exist, would evaporate quickly. The mathematics describing time dilation near black holes is precise and has been confirmed through many observations. Gravitational time dilation has been measured near Earth, where the effect is tiny but detectable. Clocks on GPS satellites run faster than clocks on the ground by about 38 microseconds per day because they are farther from Earth's mass. This difference must be corrected for GPS systems to work accurately. Near black holes, the same effect becomes extreme, stretching time by enormous factors. The concept of an event horizon, a boundary beyond which events cannot affect outside observers, emerges naturally from general relativity. The horizon forms whenever enough mass concentrates in a small enough region. For a non-rotating object, the critical radius is the Schwarzschild radius, equal to twice the gravitational constant times the mass divided by the speed of light squared. Pack any amount of mass inside its Schwarzschild radius and an event horizon forms. For Earth, this radius is about 9 millimeters. For the Sun, about 3 kilometers. Earth and the Sun are much larger than these radii, so they are not black holes. A stellar remnant that cannot support itself against gravity collapses past its Schwarzschild radius and forms a black hole. Time near a black hole flows according to the local geometry of space-time. Observers at different positions experience time at different rates, yet all are correct about what they measure locally. Only when comparing measurements do the differences appear. This relativity of time, this observer dependence, lies at the heart of Einstein's theory. There is no absolute time, no universal clock ticking the same for everyone. Time is woven into the fabric of space-time, and gravity curves that fabric, causing time itself to flow at different rates in different places. A neutron star represents matter compressed to its absolute limit. These objects form when massive stars explode as supernovae and the core collapses under its own gravity until neutrons themselves are pressed together as tightly as possible. The density that results challenges comprehension. A single teaspoon of neutron star material would have a mass of about 1 billion metric tons. To put this in perspective, 1 billion metric tons is roughly the mass of all vehicles on Earth. Combined, every car and truck and bus and motorcycle. Compress all of that into a volume that would fit on a teaspoon, a space of about 5 milliliters. This is not just dense. This is matter at the edge of what physics allows before collapsing into a black hole. The density of a neutron star averages between 300 million and 700 million metric tons per cubic centimeter. A cubic centimeter is about the size of a sugar cube. Imagine taking several 100 million metric tons and compressing it to that volume. The comparison to anything in everyday experience becomes meaningless. We have no reference point for such density. Even atomic nuclei, where protons and neutrons pack together tightly, are less dense than neutron star matter. This extreme density comes from the nature of neutron stars themselves. When a massive star's core collapses, electron degeneracy pressure, the quantum mechanical effect that prevents electrons from occupying the same space, fails to stop the collapse. Electrons are forced into protons, creating neutrons and releasing neutrinos. What remains is almost entirely neutrons, packed together at nuclear density. The neutrons themselves provide the pressure that prevents further collapse through a quantum effect called neutron degeneracy pressure. The star stabilizes at a size of about 20 kilometers in diameter, despite containing more mass than the Sun. Most of a neutron star's mass exists in the outer kilometer or so of radius. The core may contain exotic forms of matter, perhaps quark matter, where neutrons break down into their constituent quarks, or other states of matter that cannot exist anywhere else in the universe. We do not know for certain what happens at the very center of a neutron star. The conditions exceed what we can recreate in laboratories, and the physics at such densities remains uncertain. The density varies with depth. The outermost layer, the crust, consists of atomic nuclei embedded in a sea of electrons similar to the interior of a white dwarf, but much denser. Below that, the nuclei become increasingly neutron-rich and bizarre in shape, forming structures called nuclear pasta because their shapes resemble spaghetti, lasagna, and other pasta forms when visualized. Deeper still, the nuclei merge into a fluid of neutrons with a small fraction of protons and electrons. The deeper you go, the higher the density until you reach the unknown core. A neutron star's gravity at its surface would be about 200 billion times stronger than Earth's gravity. An object dropped from 1 meter above the surface would hit the ground in a few microseconds, traveling at a significant fraction of the speed of light. The escape velocity from a neutron star surface is about 150,000 kilometers per second, roughly half the speed of light. This intense gravity affects everything near the star, creating strong gravitational lensing, bending light paths into curves, allowing you to see around to the far side of the star if you could observe from nearby. The magnetic fields of neutron stars can be extraordinary. Some neutron stars, called magnetars, have magnetic fields 1 trillion times stronger than Earth's magnetic field. These are the strongest magnetic fields known in the universe. A magnetar's magnetic field would be lethal at a distance of 1,000 kilometers, powerful enough to disrupt chemical bonds in your body. The field contains more energy than the entire electromagnetic output of the sun. When these magnetic fields reconfigure, they release tremendous bursts of X-rays and gamma rays that we can detect from thousands of light years away. The rotation of neutron stars can be equally remarkable. Pulsars, neutron stars that emit beams of radiation from their magnetic poles, can spin hundreds of times per second. The fastest known pulsar rotates 716 times per second. A point on its equator moves at about 24% of the speed of light. The entire star, with a mass greater than the Sun, completes a full rotation in less than 1.5 milliseconds. This is possible only because of the star's small size and extreme density. A normal star rotating this fast would tear itself apart. These rotation rates result from conservation of angular momentum. When the massive star's core collapses from a radius of thousands of kilometers to a radius of 10 kilometers, its rotation rate increases dramatically, the same way an ice skater spins faster when pulling in their arms. The neutron star ends up spinning much faster than the original star core. Over time, the rotation gradually slows as the star loses energy through its radiation, but the slowdown can take millions or billions of years. Neutron stars cool slowly. When first formed in a supernova, the core temperature can be several 100 billion Kelvin. The star radiates this heat away as neutrinos initially, since neutrinos can escape from the interior while photons are trapped by the dense matter. Over millions of years, the temperature drops to a few million Kelvin at the surface, cool enough that most radiation is in X-rays rather than gamma rays. Old neutron stars, billions of years old, might have surface temperatures of only a few 100,000 Kelvin, though we have difficulty detecting such cool, old neutron stars unless they happen to be pulsars with active magnetic fields. The mass of a neutron star has limits. Too little mass, less than about 1.4 solar masses, and the object would be a white dwarf instead, supported by electron degeneracy pressure. Too much mass, more than about 2 to 2.5 solar masses depending on the equation of state of neutron matter, and gravity overcomes neutron degeneracy pressure, causing collapse to a black hole. Most known neutron stars have masses between 1.3 and 2 solar masses, safely within the stable range. The equation of state of neutron star matter, the relationship between pressure and density, remains one of the major unsolved problems in astrophysics. Different theoretical models predict different maximum masses and different internal structures. Observations of neutron stars, particularly measurements of their masses and radii, help constrain these models. Recent observations of neutron star mergers, detected through gravitational waves and electromagnetic radiation, have provided new data on how neutron star matter behaves under extreme conditions. When two neutron stars merge, as observed in August 2017, the collision creates conditions we cannot replicate on Earth. The stars spiral together, tidally deformed by each other's gravity, until they collide at a significant fraction of the speed of light. The merger produces gravitational waves that carried information about the star's masses and deformability. It also produced a kilonova, an explosion powered by the radioactive decay of heavy elements formed in the merger. The event scattered perhaps several Earth masses of gold, platinum, and other heavy elements into space. The interior of a neutron star remains the densest stable matter in the universe. Black holes have singularities where density becomes infinite according to general relativity, but these are not stable in the sense that they cannot be observed or studied in the same way. Neutron stars represent the densest matter we can actually observe and characterize, the limit of compression before matter gives up and collapses to a black hole. Living near a neutron star would be impossible, not just because of gravity and radiation, but because the tidal forces would be immense. The difference in gravitational pull between your head and feet, if you could somehow stand on a neutron star surface, would be billions of times your body weight. You would be stretched into a strand of atoms even before considering the lethal radiation and heat. Neutron stars are fascinating to study from a distance, but represent some of the most hostile environments imaginable. The sheer density of neutron stars means they pack an enormous amount of mass into a very small volume. A neutron star with 1.4 times the Sun's mass might have a radius of only 10 to 12 kilometers. The entire star, more massive than the Sun, would fit comfortably within the city limits of a large metropolitan area. This compression of stellar mass into such a small size creates all the extreme properties neutron stars exhibit, from their intense gravity to their rapid rotation to their powerful magnetic fields. The Voyager 1 spacecraft, launched in September 1977, is now the most distant human-made object. As of the beginning of 2026, it travels through interstellar space at a distance of more than 25 billion kilometers from Earth. This distance increases by roughly 500 million kilometers each year, about the distance from Earth to the asteroid belt, as the spacecraft continues moving at about 17 kilometers per second. Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, in August 2012. This marked the first time a human-made object entered interstellar space. The crossing was detected through changes in the charged particle environment and through measurements of the local magnetic field. Beyond the heliopause, the spacecraft encountered the plasma of interstellar space, material between the stars rather than material streaming from the Sun. The spacecraft carries a golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. The record includes greetings in 55 languages, music from different cultures and eras, sounds of nature including wind, thunder, and animal calls, and 116 images showing scientific concepts, human anatomy, architecture, and scenes from nature. The record also contains instructions, diagrams showing how to play it, and where Earth is located relative to nearby pulsars. Voyager 1 will never return. It follows a trajectory taking it out of the solar system at an angle to the ecliptic plane. Its path will carry it near other stars, though these encounters will occur in the distant future. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of the star Gliese 445. It will still be functioning as a spacecraft, though its instruments powered down long ago when the plutonium in its radioisotope thermoelectric generators decayed too much to provide sufficient electricity. The power supply limits Voyager 1's operational lifetime. The spacecraft generates electricity from the heat of decaying plutonium-238. The plutonium has a half-life of 87.7 years, meaning half of it decays every 87.7 years. Less. Plutonium means less heat and less electricity. To conserve power, mission controllers have systematically shut down non-essential systems over the years. By 2025, only a few instruments remained active. The spacecraft will likely lose the ability to communicate with Earth sometime in the mid-2020s when power levels drop below what is needed to operate the transmitter. Even after communication ceases, Voyager 1 will continue traveling. Its trajectory through the galaxy is predictable for hundreds of thousands of years. The spacecraft experiences very little force in interstellar space, just the occasional gravitational nudge from distant stars and the gentle radiation pressure of starlight. It will coast through the void, a silent artifact of a civilization that briefly reached out to touch the space between stars. Voyager 2, launched 16 days before Voyager 1, follows a different trajectory and remains in contact with Earth, though it, too, travels through interstellar space after crossing the heliopause in November 2018. Voyager 2 is about 20 billion kilometers from Earth, slightly closer than Voyager 1 because it travels along a different path at a slightly lower velocity relative to the Sun. Both voyages used gravitational assists from planets to gain speed. Voyager 1 flew by Jupiter and Saturn, using the planet's gravity to increase its velocity and change direction. Voyager 2 flew by all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, the only spacecraft to visit the latter 2 worlds. These encounters provided the velocity needed to escape the Sun's gravity and reach interstellar space. The journey to interstellar space took 35 years for Voyager 1. This demonstrates the vast scale of even the local solar environment. The heliopause lies about 120 astronomical units from the Sun, 120 times the Earth-Sun distance. Light from the Sun takes about 16.5 hours to reach this boundary. The voyages, traveling much slower than light, took decades. Communication with the voyages requires patience. A radio signal from Earth takes about 22.5 hours to reach Voyager 1 at its current distance. The spacecraft's response takes another 22.5 hours to return. Any command sent to the spacecraft will not receive confirmation until 45 hours later. This light travel time will increase as the spacecraft moves farther away, eventually making communication impossible not because of power limitations, but simply because the time delay becomes impractical. The Voyagers use the Deep Space Network, a collection of large radio antennas in California, Spain, and Australia to communicate with Earth. These antennas can detect the incredibly weak signals from the spacecraft, only about 20 watts, the power of a refrigerator light bulb, transmitted across billions of kilometers of space. The key signal has spread out so much by the time it reaches Earth that only a tiny fraction of the original power arrives, but the sensitive receivers can still decode the data. Data returns slowly from the voyages. The transmission rate is only 160 bits per second, a tiny fraction of modern internet speeds, because the weak signal cannot support faster communication. Each image or data packet takes a long time to transmit. The spacecraft sends back measurements of cosmic rays, magnetic fields, plasma density and temperature, and other properties of interstellar space. The discoveries continue. Voyager 1 detected a boundary region at the heliopause where solar and interstellar magnetic fields interact. It measured unexpected properties of the interstellar medium, including a density of charged particles higher than some models predicted. These observations help us understand the environment between stars, a region we cannot easily study except by sending spacecraft into it. Both voyages carry the same golden record. The choice to include the same content on both spacecraft was deliberate. It increases the chances that at least one record survives encounters with interstellar dust, cosmic rays, or other hazards. The records are mounted on the spacecraft's side, protected from direct impact with the spacecraft's trajectory, but still exposed to the space environment. The golden record cover includes a diagram showing how to play it, instructions based on fundamental physics that should be understandable to any technological civilization. It depicts the transition of hydrogen between its two lowest energy states, a universal constant, and uses this to define units of time and frequency. Other diagrams show the location of our solar system relative to 14 pulsars, using the pulsar's unique spin periods as identifiers. The probability of either Voyager being found by an alien civilization is vanishingly small. Space is vast, the spacecraft are small. They follow trajectories that will not bring them particularly close to any known star system for tens of thousands of years. Even if intelligent life exists elsewhere in our galaxy, and even if such life has the technology to detect small objects in interstellar space, the chances of them finding a Voyager spacecraft approach zero. The golden records are more symbolic than practical, a message to ourselves about who we are and what we value. The Voyagers represent the beginning of humanity's expansion beyond the solar system, not in person, but through our instruments and messages. They demonstrate that we can build machines robust enough to operate for decades in the hostile environment of space, that we can navigate them across billions of kilometers with precision, and that we can maintain communication across distances that challenge our technology. Everything we learn from these spacecraft improves our understanding of the space our solar system moves through and what any future interstellar mission will encounter. The silence will come eventually. The plutonium will decay. The power will drop. The transmitters will stop. The Voyagers will go quiet, drifting through interstellar space with no way to tell us what they experience. But they will continue, carrying their golden records, moving through the galaxy for millions or billions of years unless they collide with something or fall into a star. They are, in a sense, immortal, preserved by the vacuum and cold of deep space far better than any artifact could be preserved on Earth. Galaxies rotate, but not the way solid objects rotate. A spiral galaxy like the Milky Way does not spin as a unit. Different parts rotate at different speeds. Stars near the galactic center complete an orbit much more quickly than stars in the outer regions, even though the inner stars travel shorter distances. This is called differential rotation, and it shapes the structure we observe. The Sun orbits the center of the Milky Way at a speed of about 220 kilometers per second. This seems fast, but the orbit is vast. The Sun sits about 26,000 light-years from the galactic center. At its current speed, it takes approximately 230 million years to complete one orbit. Since the Sun formed 4.6 billion years ago, it has completed about 20 orbits around the galaxy. Stars closer to the galactic center orbit faster in an absolute sense, completing their orbits in less time, though they may move slower through space than the Sun. This depends on the mass distribution within their orbital radius. In the inner few thousand light-years, where the galactic bulge concentrates most of the mass, orbital speeds can be higher. A star 1,000 light-years from the galactic center might orbit in just a few million years. Stars in the outer regions of the galaxy orbit more slowly and take much longer to complete an orbit. A star 40,000 light-years from the galactic center might take 500 million years to orbit once. The orbital period increases with distance, though not as quickly as it would if most of the galaxy's mass were concentrated at the center. The presence of dark matter in the galactic halo affects the rotation curve, keeping orbital velocities higher at large distances than expected from visible matter alone. This differential rotation should, in theory, wind up the spiral arms. If the arms were made of the same stars rotating at different speeds, the arms would become more tightly wound over time, eventually wrapping many times around the galaxy. But observations show spiral arms maintain a relatively open structure. This paradox led to the development of spiral density wave theory. According to density wave theory, spiral arms are not permanent structures made of specific stars. Rather, they are waves of compression moving through the galactic disk. Stars and gas clouds orbit the galactic center, but the spiral pattern itself rotates at a different rate. A pattern speed that stays constant with radius rather than changing like the orbital speeds of matter. Stars enter a spiral arm, slow down slightly due to the increased gravitational attraction, then exit the arm and speed up again. This is analogous to a traffic jam on a highway. Individual cars move through the jam, entering from behind, slowing down, then exiting the front and speeding up again. The jam itself, the pattern of compressed traffic, can move at a different speed than the individual cars, or even remain stationary while cars flow through it. Spiral arms work similarly. They are regions of enhanced density, traffic jams in the galactic disk, where stars temporarily congregate. The compression in spiral arms triggers star formation. As gas clouds enter the arm, they are compressed by the increased density. This compression can cause clouds to collapse and form new stars. The most massive of these stars are bright and blue, shining brilliantly for only a few million years before exploding as supernovae. These bright young stars trace out the spiral arms, making them visible. By the time these stars die, they have exited the spiral arm and dispersed into the disk, but new stars have formed within the arm to take their place. This is why spiral arms appear blue. They are not intrinsically bluer than other parts of the galaxy. They just contain a higher proportion of young, massive blue stars. Older, redder stars exist in the arms too, but the young stars outshine them, creating the visual impression of blue spiral structures. Between the arms, where star formation is less active, the older, redder stars dominate the light. The Milky Way has two major spiral arms and several smaller arm segments or spurs. The major arms, the Perseus and Scutum Centaurus arms, extend across the galaxy. The Sun sits near the inner edge of a smaller arm called the Orion Spur, a minor arm between two major ones. This location, about midway out from the center, provides a relatively stable environment with moderate star formation rates and a lower density than the inner galaxy. The rotation of the galaxy causes the Sun to move through space at a considerable velocity relative to the local standard of rest, a notional reference frame defined by the average motion of nearby stars. Relative to the cosmic microwave background, the Sun moves at about 370 kilometers per second when you account for the Sun's orbital motion, the Milky Way's motion through the local group of galaxies, and the local group's motion through space. Most of this velocity comes from the galactic orbit, but contributions from larger-scale motions add up. The galactic disk has a thickness of about 1,000 light-years for the thin disk where most stars reside. The Sun orbits up and down through this disk with a period of about 64 million years, a vertical oscillation superimposed on its circular orbit. Currently, the Sun sits roughly 90 light-years above the midplane of the disk, moving upward. It will reach a maximum height of about 250 light-years above the midplane before falling back down, crossing the midplane, and descending to a similar distance below before returning. This vertical motion through the disk may influence Earth's climate and biological history. Some researchers have proposed that passages through the denser midplane regions increase the rate of comet impacts, as gravitational perturbations from molecular clouds disrupt the distant Oort cloud and send comets toward the inner solar system. The correlation between mass extinction events and vertical disk crossings is debated, with some data supporting it and other analyses finding no clear pattern. The rotation of the galaxy mixes material gradually. Stars that form in one location migrate to other locations over many orbits. The Sun formed elsewhere in the galaxy and has migrated to its current position through interactions with spiral arms and molecular clouds that altered its orbit. Many stars in the solar neighborhood originated in different parts of the galaxy and have since scattered to their current locations. This mixing ensures that the galactic disk does not maintain sharp gradients in chemical composition or other properties over billions of years. The Milky Way's rotation rate is not constant over time. As the galaxy ages, its rotation can change due to mergers with smaller galaxies, accretion of gas, and the slow evolution of its structure. The Milky Way is currently absorbing several smaller dwarf galaxies, including the Sagittarius dwarf elliptical galaxy. The disruption caused by these mergers injects energy and angular momentum into the disk, affecting rotation patterns. Dark matter dominates the mass of the galaxy, outweighing visible matter by approximately 5-to-1. Most of this dark matter resides in an extended halo surrounding the visible disk. This dark matter provides much of the gravitational force governing the galaxy's rotation. The rotation curve, a plot of orbital velocity versus distance from the galactic center, remains flat or even slightly increases in the outer regions, contradicting what would be expected if only visible matter were present. This discrepancy provides strong evidence for dark matter. Different components of the galaxy rotate at different rates. The disk, containing most of the stars and gas, rotates relatively quickly. The central bulge, containing older stars, rotates as well, but with more complex kinematics, including random motion in addition to rotation. The stellar halo, containing the oldest stars, has very little net rotation. Stars in the halo follow elliptical orbits with random orientations, creating a cloud of stars that does not participate in the organized rotation of the disk. The supermassive black hole at the center of the Milky Way, Sagittarius A star, sits at the rotational center of the galaxy. With a mass of about 4 million solar masses, It provides a gravitational anchor that defines the center point of the rotation. Stars very close to Sagittarius. A star, within a fraction of a light year, orbit it directly, their motion dominated by the black hole's gravity. These stars have been tracked over decades, their orbits confirming the black hole's mass and testing general relativity in the strong gravity regime. Understanding the galaxy's rotation helps us determine its mass, structure, and history. The rotation curve provides a direct probe of the mass distribution, both visible and dark. The spiral structure reveals the density wave pattern and the rate of star formation. The vertical oscillations trace the gravitational potential of the disk. All of these measurements, combined with observations of other galaxies, build our picture of how galaxies form, evolve, and organize themselves under the influence of gravity and dark matter. The observable universe extends approximately 46 billion light-years from Earth in every direction. This defines a spherical region, centered on us, with a diameter of about 93 billion light-years. This is not the total size of the universe. The universe may be infinite, extending forever beyond what we can observe. The observable universe is simply the portion from which light has had time to reach us since the Big Bang. The confusion often arises from the age of the universe. If the universe is 13.8 billion years old, why can we see objects 46 billion light-years away? The answer lies in expansion. When the light from very distant objects began its journey toward us, those objects were much closer. As the light traveled, space expanded, increasing the distance to the source. By the time the light reaches us, the object that emitted it is now 46 billion light-years away, even though the light has been traveling for less than 13.8 billion years. The edge of the observable universe corresponds to the cosmic microwave background, the light released at recombination 380,000 years after the Big Bang. We cannot see farther than this using electromagnetic radiation because the universe was opaque before recombination. The cosmic microwave background represents our ultimate visual horizon. The matter that emitted this radiation is now about 46 billion light-years away due to expansion. The observable universe contains approximately 2 trillion galaxies. This is an estimate based on deep surveys that count galaxies in small patches of sky and extrapolate to the full sky. Each galaxy contains tens of millions to hundreds of billions of stars. The total number of stars in the observable universe is roughly 10 to the power of 24, a trillion stars. These numbers are almost incomprehensibly large, yet they describe a finite, observable region of space. The expansion of the universe means the observable universe grows over time. As time passes, light from more distant regions reaches us. The observable universe increases in radius by 1 light-year every year as light travels 1 additional light-year closer to us. However, because the universe also expands during this time, the actual radius of the observable universe increases more slowly when measured in co-moving coordinates, which account for expansion. The physical size of the observable universe, measured in light-years at the present time, reflects both the age of the universe and the expansion history. If the universe had not expanded, the observable universe would extend only 13.8 billion light-years, the light travel distance. Expansion stretched the distances, placing the sources of the most distant light we see at their current distance of 46 billion light-years. Beyond the observable universe lies more universe. We cannot see it, not because there is nothing there, but because light from those regions has not had time to reach us yet. The universe could extend infinitely, filled with galaxies and stars like the ones we observe, or it could have a finite size with some kind of boundary or unusual geometry. Current observations suggest the universe is very close to geometrically flat, which is consistent with infinite extent, but does not prove it. The shape of the universe depends on its total energy density. If the density exactly equals the critical density, about 5.7 atoms of hydrogen per cubic meter averaged over all space, the universe is geometrically flat and likely infinite. If the density is higher, the universe has positive curvature and could be finite, shaped like the three-dimensional surface of a four-dimensional sphere. If the density is lower, the universe has negative curvature and would be infinite, shaped like a saddle extending forever. Measurements indicate the density is very close to critical, within about 1%, suggesting a flat, infinite universe. The particle horizon defines the boundary of the observable universe. This is the distance light could have traveled since the Big Bang, accounting for expansion. Currently, this distance is about 46 billion light-years. In the future, the particle horizon will extend farther as light from more distant sources reaches us. However, because of accelerating expansion, there is also a cosmic event horizon beyond which we will never see objects no matter how long we wait. The cosmic event horizon exists because of dark energy. If the expansion accelerates at an increasing rate, light from sufficiently distant regions will never reach us. Space expands faster than light can cross it on these scales. The cosmic event horizon lies at about 63 billion light-years, currently farther than the particle horizon. We can see objects out to the particle horizon, but not yet to the event horizon. In the future, as expansion continues, objects beyond the event horizon will disappear from view as their light gets redshifted to undetectable wavelengths. Galaxies we currently observe will eventually vanish. In about 100 billion years, galaxies beyond our local group will have receded so far that their light cannot reach us. The Milky Way and its nearest neighbors will remain visible, bound together by gravity, but the rest of the universe will fade away. Future astronomers in that era would see only their local galaxy group surrounded by darkness, with no evidence of the broader universe. They would not know about the Big Bang, cosmic expansion, or the existence of billions of other galaxies unless they found records left by earlier civilizations. The volume of the observable universe increases as the radius grows. Currently, the observable universe contains about 4 × 10 to the power of 80 cubic meters of space. This volume grows as light from farther sources reaches us, but expansion also increases the distance to objects we can already see. The combination of these effects determines how the observable universe evolves over time. Within the observable universe, structure exists at many scales. Individual stars cluster into galaxies. Galaxies cluster into groups and clusters. Clusters form superclusters. Superclusters outline enormous filaments and sheets surrounding cosmic voids. This hierarchy of structure reflects the initial density fluctuations of the early universe, amplified by billions of years of gravitational attraction. The largest known structures in the universe span hundreds of millions of light-years. The Hercules Corona Borealis Great Wall is a superstructure of galaxies extending about 10 billion light-years across. Structures this large challenge our understanding of cosmology because the early universe was so uniform. How could such enormous structures form from the tiny density fluctuations observed in the cosmic microwave background? The answer involves dark matter, which began clumping earlier than ordinary matter, and the long time scales over which gravitational attraction worked to pull matter together. The distribution of matter in the observable universe appears statistically uniform when averaged over very large scales, hundreds of millions of light-years or more. Look at any sufficiently large volume, and it contains about the same number of galaxies as any other similar volume. This uniformity is called the cosmological principle, the assumption that the universe is homogeneous and isotropic when viewed at large enough scales. Observations support this principle. The universe looks roughly the same in all directions when we examine large enough regions. Light from different distances shows us the universe at different times. When we observe a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago when the universe was less than 4 billion years old. The most distant galaxies, seen as they were less than 1 billion years after the Big Bang, appear small, irregularly shaped, and actively forming stars. These young galaxies evolved into the large, mature galaxies we see nearby. This time dimension of observation allows us to study cosmic history. By comparing galaxies at different distances, we observe how galaxies change over time. Nearby galaxies are old, containing mostly red stars with little ongoing star formation. Distant galaxies are young, filled with active star formation, appearing blue and chaotic. The transition between these states happened gradually over billions of years as galaxies consumed their gas supplies and star formation declined. The observable universe will look different in the future, not just because more distant light will have arrived, but because the universe itself continues to evolve. Stars will age, gas will be consumed, star formation will decline. Eventually, in trillions of years, the last stars will form. After that, the universe will gradually darken as existing stars burn out and no new ones replace them. The observable universe of the far future will be a much darker, emptier place than what we see today. The edge of the observable universe is not a physical edge. There is no boundary or wall. It simply represents the limit of what we can observe from our location at this time. An observer in a galaxy near the edge of our observable universe would have their own observable universe, centered on them, extending 46 billion light-years in all directions from their location. Their observable universe would overlap with ours, but also extend into regions we cannot see. Each location in the universe has its own observable universe, its own particle horizon. The observable universe contains all the galaxies and matter we can potentially interact with using light or any other signal. Objects beyond the observable universe are permanently beyond our reach, not just difficult to see but impossible to affect or receive signals from. As expansion continues and the event horizon becomes relevant, even some objects currently within our observable universe will slip beyond our ability to ever receive new light from them. Measuring the size of the observable universe requires careful definition of distance. The co-moving distance, which accounts for expansion and represents where an object is now, gives 46 billion light-years. The light travel distance, which represents how far light has actually traveled to reach us, gives about 13.8 billion light-years. The proper distance, which would be measured by laying rulers end to end at a single instant of cosmic time, equals the comoving distance. Each distance definition serves different purposes and gives different numbers. The concept of the observable universe reminds us of our limited perspective. We see only a finite fraction of all that exists. The universe extends beyond what we can observe, filled with galaxies and structures we will never see. Our location provides one particular view, one particular observable bubble within the larger cosmos. Other observers in other galaxies see their own bubbles, overlapping with ours but not identical. No single observer sees everything. The totality of the universe exceeds any one perspective. In space, there is no sound. This is not because sound waves cannot be produced. It is because there is no medium to carry them. Sound requires matter, molecules of gas or atoms or particles that can vibrate and transmit pressure waves. Space, particularly the near vacuum of interstellar and intergalactic regions, contains so few particles that sound cannot propagate. On Earth, sound travels through air at about 343 meters per second at sea level. The air molecules vibrate, creating regions of compression and rarefaction that move through the atmosphere. Your ear detects these pressure variations as sound. This process requires a certain minimum density of matter. Below that density, the distance between molecules becomes too great for efficient transmission of vibrations. In the interstellar medium, with an average density of about 1 million particles per cubic meter, sound could theoretically travel, but it would be so weak and travel so slowly that it bears little resemblance to sound as we experience it. The wavelength of any sound wave would be enormous, many kilometers or more, and the frequency would be incredibly low, far below the range of human hearing. These are not sound waves in any practical sense, but extremely low-frequency pressure oscillations in the tenuous gas between stars. In denser regions like molecular clouds, where densities can reach 1 trillion particles per cubic meter, sound-like phenomena become more relevant. Shock waves from supernovae propagate through these clouds, compressing the gas and triggering star formation. These shock fronts are pressure waves, technically sound waves, but they travel through gas thousands of times thinner than Earth's atmosphere. The speed of sound in the interstellar medium varies with temperature and composition, but typically ranges from a few kilometers per second to tens of kilometers per second. The absence of sound in vacuum makes space profoundly quiet from a human perspective. If you could float in interstellar space, you would hear nothing. No matter what events occurred around you, no sound would reach your ears. A nearby supernova, despite releasing enormous energy, would be silent. You would see the light, feel the radiation, be destroyed by the energy, but you would not hear it. This silence contrasts sharply with the rich electromagnetic spectrum of space. While sound cannot travel, light and other forms of electromagnetic radiation propagate easily through vacuum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays all travel through empty space at the speed of light, requiring no medium. Space is filled with electromagnetic radiation from countless sources, creating a complex environment invisible and inaudible to human senses, but detectable with instruments. The cosmic microwave background bathes all of space in microwave radiation. This radiation carries no sound but has a characteristic spectrum corresponding to a temperature of 2.726 Kelvin. Radio emissions from pulsars sweep across space, creating pulses of radio waves timed with precision better than atomic clocks. X-rays from hot gas in galaxy clusters reveal the presence of dark matter through gravitational effects. Gamma rays from distant blazars arrive after traveling for billions of years across the expanding universe. Some astronomical phenomena create pressure waves in tenuous plasma that could be considered analogous to sound. The Sun produces acoustic oscillations, vibrations that move, through the solar interior and surface. These oscillations have been studied through helioseismology, revealing the Sun's internal structure. The frequencies are very low, periods of about 5 minutes, creating waves that ripple across the solar surface. If you could somehow hear these oscillations, they would be deep rumbles far below the range of human hearing. Black holes can create sound waves in surrounding gas. As matter falls into a black hole, it heats and emits energy that drives shock waves through nearby material. These waves can be thought of as sound, pressure variations propagating through the accretion disk and surrounding medium. The Perseus galaxy cluster contains a supermassive black hole that has apparently created sound waves in the surrounding hot gas. The waves have a period of about 10 million years and have displaced vast quantities of gas, but translated to a frequency humans could hear, they would represent a B-flat note 57 octaves below middle C. Gravitational waves represent a different kind of wave, distortions in space-time itself rather than pressure waves in matter. When two black holes merge, they create gravitational waves that travel at the speed of light, carrying energy away from the system. These waves have been detected by instruments like LIGO and Virgo. The waves from a black hole merger last only a fraction of a second and sweep upward in frequency as the black holes spiral together, creating a characteristic chirp. Scientists have converted these gravitational wave signals into sound files that can be played, allowing us to hear the merger in a sense, though the actual waves are not sound and do not require a medium. The conversion of non-audible phenomena into sound, called sonification, has been used to make various astronomical datasets accessible to human hearing. Light curves from variable stars have been converted to musical tones. The radio emissions from pulsars have been played as rhythmic pulses. The cosmic microwave background temperature map has been converted to sound by mapping temperature to pitch. These are artistic or educational representations, not actual sounds from space, but they can convey information in a different sensory modality. Electromagnetic waves and sound waves differ fundamentally. Sound is a longitudinal wave with compressions and rarefactions parallel to the direction of travel. Electromagnetic waves are transverse, with electric and magnetic fields oscillating perpendicular to the direction of propagation. Sound requires a medium and travels relatively slowly. Electromagnetic waves require no medium and travel at the universal speed limit, the speed of light in vacuum. The speed of sound in any medium depends on the medium's properties, its density, and how easily it compresses. In denser materials, sound typically travels faster. In steel, sound moves at about 6,000 meters per second. In water, about 1,500 meters per second. In air, at room temperature, about 343 meters per second. In the thin gas of the interstellar medium, sound would travel much more slowly, though the exact speed depends on the temperature and composition of the gas. The silence of space is absolute in regions far from stars and galaxies. No vibrations disturb the vacuum. No pressure waves propagate. The occasional atom drifts by, but there is no collective motion of particles creating sound. This is a silence deeper than any achievable on Earth, where even the quietest chamber still contains air molecules creating faint thermal noise. In interstellar space, no such background exists. The silence is complete. Yet space is not inactive or empty in any meaningful sense. Cosmic rays streak through at nearly the speed of light. Neutrinos pass through everything, barely interacting. Photons from distant stars and galaxies cross the void. Magnetic fields thread through the plasma. Gravitational waves ripple through space-time. All of this activity occurs silently, without sound, in a medium that cannot support acoustic waves. The universe is filled with energy and motion, just not the kind that creates sound. This fundamental silence will persist as long as the vacuum of space exists. As the universe expands and matter spreads thinner, the regions where sound could propagate will shrink. The dense molecular clouds will eventually be consumed in star formation. The gas will disperse. In the far future, when galaxies have consumed most of their gas and star formation has ceased, even the tenuous interstellar medium will be largely gone. The universe will become even more silent than it is now, a vast expanse where electromagnetic waves cross paths, but no sound exists. The timescales of cosmic processes dwarf human experience. Stars live for millions, billions, even trillions of years depending on their mass. Galaxies evolve over billions of years. The universe itself is 13.8 billion years old. These durations challenge comprehension, yet they represent fundamental aspects of how the cosmos operates. Nothing in space happens quickly by our standards. Everything unfolds with a patience that makes human lifetimes seem like brief flickers. The Sun has existed for about 4.6 billion years. It formed from a collapsing molecular cloud, gradually pulling itself together through gravity until the core became hot and dense enough to initiate fusion. This process took several tens of millions of years, fast by cosmic standards, but incomprehensibly slow by human ones. Once fusion began, the Sun settled into a stable state where it has remained, fusing hydrogen into helium in its core, maintaining a balance between gravity pulling inward and pressure pushing outward. The Sun will continue this stable phase for about another 5 billion years. It is almost exactly halfway through its main sequence lifetime. Eventually, the hydrogen in the core will be exhausted. The core will contract and heat up, while the outer layers will expand. The Sun will become a red giant, swelling to perhaps 100 times its current diameter, engulfing the inner planets, including possibly Earth. This red giant phase will last several 100 million years before the Sun sheds its outer layers and contracts to become a white dwarf. As a white dwarf, the Sun will slowly cool over trillions of years, radiating away its remaining heat into space. White dwarfs do not generate new energy. They simply release the thermal energy they contain. The cooling process is extremely slow because the Sun will have only a small surface area as a white dwarf, perhaps the size of Earth. Small surface area means slow heat loss. The Sun will remain warm enough to glow visibly for tens of billions of years, longer than the current age of the universe. Eventually, in the unimaginably distant future, it will cool to become a black dwarf, a cold, dark sphere of degenerate carbon and oxygen. More massive stars live much shorter lives. A star 10 times the Sun's mass might live only 20 million years. It burns through its hydrogen fuel much faster because it must maintain higher core temperatures to support its greater mass against gravity. When such a star exhausts its hydrogen, it quickly fuses heavier elements, progressing through helium, carbon, oxygen, neon, silicon, and finally iron. The entire process from main sequence star to supernova explosion can occur in less than 10 million years once fusion begins. Less massive stars live much longer. A red dwarf with 1/10 the Sun's mass might live for 10 trillion years. These stars are so small and cool that they fuse hydrogen very slowly, sipping their fuel over timescales vastly longer than the current age of the universe. The smallest red dwarfs formed in the early universe are still on the main sequence today, barely changed since they ignited. They will continue fusing for trillions of years into the future. No red dwarf has ever died of old age. The universe is not old enough. Galaxies collide over hundreds of millions to billions of years. The Milky Way and Andromeda are approaching each other at about 120 kilometers per second. They will collide in about 4 billion years. The collision will not involve stars crashing into each other. Stars are so far apart that two galaxies can pass through each other with almost no direct stellar collisions. Instead, the gravitational interactions will disrupt both galaxies, flinging stars into new orbits, triggering bursts of star formation as gas clouds collide, and eventually merging the two galaxies into a single, larger elliptical galaxy. This merger will take several billion years from first contact to final coalescence. The galaxies will pass through each other, then separate, then swing back together due to gravity. Multiple passages will occur, each one further disrupting both galaxies before they finally merge. The entire process will span perhaps 3 or 4 billion years. By the time it is complete, the Sun will be near the end of its main sequence lifetime, possibly already entering its red giant phase. Superclusters, the largest gravitationally bound structures in the universe, form over even longer timescales. The Laniakea supercluster, which contains the Milky Way, spans about 500 million light-years. Material within this supercluster is slowly moving toward the central concentration, a region called the Great Attractor. This motion has been occurring for billions of years and will continue for billions more. The timescale for structures this large to collapse under gravity exceeds the current age of the universe. The universe itself will exist for an unimaginably long time, possibly forever if it expands eternally. The current era, with stars forming and shining, is just the beginning. In about 100 trillion years, star formation will cease as galaxies exhaust their gas supplies. The universe will enter the degenerate era, dominated by slowly cooling white dwarfs and long-lived red dwarfs. This era will last until about 10 to the power of 40 years from now, when even the longest-lived stars will have died. After the degenerate era comes the black hole era, from about 10 to the power of 40 years to 10 to the power of 100 years. During this period, black holes dominate the universe's mass. Dead stars occasionally collide and fall into black holes. Planets are disrupted by gravitational encounters. Black holes slowly evaporate via Hawking radiation, a process so slow that a solar mass black hole would take 10 to the power of 67 years to evaporate completely. After the black hole era, assuming protons decay on very long timescales, comes the dark era. The universe contains only photons, neutrinos, electrons, and positrons, all drifting apart due to expansion. The temperature of the universe approaches absolute zero. Nothing happens except the gradual expansion of space. This era has no defined endpoint. It continues forever, or until something we do not currently understand changes the situation. These timescales illustrate the cosmic patience required for large-scale processes. The evolution of stars, galaxies, and the universe itself operates on timescales billions or trillions of times longer than human civilization has existed. From the perspective of the cosmos, human history occupies an instant, a brief moment within the first 1% of the universe's existence so far. Consider the orbit of the Sun around the galaxy. At 230 million years per orbit, the Sun has completed only about 20 orbits since it formed. Complex life on Earth has existed for only about 2 or 3 galactic orbits. Human civilization has existed for a tiny fraction of 1 orbit. The galaxy has rotated only about 1 degree since the invention of writing. By cosmic measures, everything in human history happened essentially simultaneously. The patience of cosmic timescales means change occurs slowly. Galaxies evolve gradually over billions of years. Stars age over millions or billions of years. Planetary orbits remain stable for billions of years. This stability allows for the existence of long-lived systems like Earth's biosphere, which has persisted for over 3 billion years despite numerous catastrophes. The slow pace of cosmic change provides a stable environment on human timescales, even though the long-term evolution continues inexorably. Yet, some cosmic events happen quickly. Supernovae explode in seconds. The core collapse of a massive star, once it begins, completes in less than a second. Neutron stars merge in a fraction of a second. Black holes can form in milliseconds. These events are catastrophic releases of energy that have been building up for millions or billions of years. The star spends millions of years fusing elements, storing gravitational energy before releasing it all in an instant. The contrast between the slow accumulation of conditions and the rapid release of energy characterizes many cosmic processes. A molecular cloud collapses slowly over millions of years, then fragments and forms stars in just hundreds of thousands of years. A black hole binary system spirals together over millions of years, then merges in a fraction of a second. The preparation is slow, the culmination rapid. Understanding these timescales changes one's perspective. Human concerns operate on timescales of seconds to decades. Civilizations last centuries to millennia. Geological processes operate on millions to billions of years. Cosmic processes span billions to trillions of years or more. Each scale has its own relevant phenomena. The cosmos operates on timescales we can barely conceive, and it will continue long after humanity is gone, continuing its slow evolution toward an increasingly empty, cold future. All of these facts, these measurements and descriptions, these vast distances and long durations, point towards something fundamental about the universe. It is large beyond imagination. It is old beyond everyday comprehension. It contains structures and processes operating on scales that dwarf human experience. Yet it follows laws we can understand. The physics governing the behavior of atoms in a laboratory on Earth also governs the cores of stars and the expansion of space itself. The universe is not chaotic. It is ordered, following consistent rules. Gravity works the same everywhere. Light travels at the same speed in all directions. The fundamental constants do not change with location or time, as far as we can tell. This consistency allows us to observe distant objects and interpret what we see, to calculate the properties of black holes we will never visit, to predict the evolution of stars that will live trillions of years into the future. The emptiness of space, the patient expansion, the ancient light still traveling, the extreme densities of neutron stars, the time dilation near black holes, all of these phenomena are real and measurable. They are not abstractions or theoretical possibilities. They exist, and we have observed them, measured them, confirmed them through multiple independent methods. The universe reveals itself to careful observation, rewarding patience with understanding. Consider what you have encountered in this exploration. The temperature of the cosmic microwave background, 2.726 Kelvin, a number known to better than 1,000th of a degree. The density of neutron stars, hundreds of millions of metric tons per cubic centimeter, matter compressed to the edge of collapse. The size of the observable universe, 93 billion light-years in diameter, containing approximately 2 trillion galaxies. The age of the universe, 13.8 billion years, measured to within 1% precision. The rotation speed of the Sun around the galaxy, 220 kilometers per second completing one orbit every 230 million years. These are not estimates or guesses. They are measurements, the results of decades of careful observation and analysis. Different methods confirm the same results. Independent teams reach the same conclusions. The evidence accumulates, building a consistent picture of a universe that is vast, ancient, expanding, and fundamentally comprehensible. The silence of space, the lack of sound in the vacuum, reminds us that our everyday experience does not always translate to cosmic scales. Sound requires a medium. Space provides none. Yet this absence does not make space empty or inactive. Electromagnetic radiation fills it. Gravitational waves pass through it. Particles stream across it at nearly the speed of light. Space is a stage on which countless processes unfold, silent but far from still. The deep future stretches ahead, timescales so long they challenge comprehension. Trillions of years will pass, stars will form and die, galaxies will merge, black holes will evaporate, the universe will continue expanding, creating more space, diluting its contents, approaching a state of maximum entropy where nothing interesting can happen anymore. This heat death lies incomprehensibly far in the future, but current evidence suggests it is our universe's ultimate fate. Yet, this distant end does not diminish the present. The universe now is filled with structure, complexity, beauty, and process. Stars shine, galaxies rotate, planets orbit. Life, at least on Earth, exists and contemplates its cosmic context. The universe is young enough that stars still form, that galaxies still collide, that interesting events still occur. We exist in what might be called the universe's prime, the era when it is complex and dynamic, before the long, slow fade into darkness and cold. The facts about deep space that we have explored tonight are not meant to disturb or unsettle. They describe a universe that operates according to consistent physical laws, a universe we can observe and understand despite its vast scales. There is a kind of peace in this understanding, a recognition that we are part of something much larger than ourselves, something that existed long before us and will continue long after, something that follows patterns we can discern and describe. The cosmic microwave background will continue cooling. Space will continue expanding. Black holes will continue distorting time. Neutron stars will continue their patient spin. Voyager 1 will continue its journey through interstellar space. The Sun will continue its orbit around the galaxy. All of these processes unfold with or without human observation, governed by physics, patient and inevitable. In contemplating these facts, these measurements, these vast scales of space and time, perhaps there is room for a kind of cosmic perspective. Our concerns, while important to us, occur within a much larger context. The universe does not notice human affairs, yet understanding the universe enriches human experience. We are, as far as we know, the universe become conscious of itself, matter organized in a way that permits reflection on its own origins and ultimate fate. The most distant light we can see left its source when the universe was a fraction of its current age. That light has traveled for over 13 billion years to reach our instruments, carrying information about conditions in the ancient cosmos. We decode this information, extracting knowledge about density fluctuations that seeded galaxy formation, about the composition of matter in the early universe, about the rate of expansion and the geometry of space. All of this from light, from photons that have journeyed across an expanding universe to arrive finally at this moment. Space extends farther than we can see, filled with galaxies we will never observe because their light has not had time to reach us or because expansion carries them away faster than their light can approach us. The universe beyond our horizon exists, contains structures and processes similar to what we observe, but remains forever hidden unless something fundamental changes about the expansion. This unknowable vastness suggests humility. There is more to the universe than any single observer can see. Yet, what we can observe is enough. 2 trillion galaxies, each containing hundreds of billions of stars. 10 to the power of 24 stars total in the observable universe. Most of those stars likely have planets. The sheer scale of the universe makes it probable that we are not alone, that life has emerged elsewhere, that other minds contemplate their cosmic context from different vantage points light years away. We do not know this for certain. We have not detected other civilizations, but the universe is large and we have examined only a tiny fraction of it. The facts about deep space are, in the end, just descriptions of what exists. The universe is what it is. Our understanding of it continues to improve, but the universe itself does not change because we measure it. It was expanding before we discovered expansion. Black holes distorted time before we described time dilation. Neutron stars had extraordinary densities before we calculated them. Our role is to observe, to measure, to understand, to place ourselves in cosmic context. This exploration of deep space facts has covered vast conceptual territory. The temperature of creation, still detectable after nearly 14 billion years. The emptiness between objects, a vacuum better than any laboratory can achieve. The ancient light from recombination, showing us the universe as it was when light first traveled freely. The patient expansion creating new space. The time dilation near black holes making time itself relative. The compressed matter of neutron stars approaching the limit of density. The farthest human artifacts carrying messages to a cosmos that may never read them. The rotation of galaxies, differentially turning over hundreds of millions of years. The size of the observable universe, a finite sphere within what may be infinite space. The silence where no sound can travel. The patience of cosmic timescales measured in billions and trillions of years. All of this exists. All of this is real. All of this continues whether we observe it or not. The universe proceeds according to its nature, vast and ancient and patient, filled with structures and processes operating on scales from the quantum to the cosmic, all woven together by fundamental laws that admit no exceptions. As we conclude this journey through the most relaxing facts about deep space, perhaps the most calming realization is simply this: the universe is understandable. Despite its vast scales, despite its ancient age, despite phenomena that seem impossible, we can observe it, measure it, describe it mathematically, and predict its behavior. The universe makes sense. It follows rules. And we, briefly, have the capacity to comprehend those rules and place ourselves within the larger cosmic story. The universe is not hostile to understanding. It reveals its secrets to patient inquiry. Every measurement refines our knowledge. Every observation adds detail to our picture of cosmic reality. The process continues, accumulating knowledge, building toward a more complete understanding of what exists and how it came to be this way. May these facts about deep space bring you some measure of perspective and peace. The universe is large, old, and patient. It operates on scales that make human concerns seem small, not in a diminishing way, but in a way that offers context. We are part of this cosmos, made of atoms forged in stars, observing the universe with tools built from understanding the same laws that govern everything from falling objects to expanding space. If you found this exploration of deep space facts valuable, if these descriptions of cosmic phenomena helped you relax or sparked your curiosity, consider subscribing to Nebula Nights. There are more journeys like this to take, more aspects of the universe to explore, more opportunities to place ourselves in cosmic context and find peace in understanding the vast scales of space and time. The universe has existed for nearly 14 billion years. It will exist for trillions more. We have only begun to explore it, to understand it, to appreciate the intricate processes that shape it. Thank you for spending this time exploring the most relaxing facts about deep space. May your rest be peaceful, your perspective expanded, and your wonder at the cosmos renewed.